Um, Hello, everyone. Thanks for joining us today. Today we have Nick. Uh, he's a PhD candidate at the University of California, San Diego, advised by Professor Wang and Professor Su. Their research focuses on developing generalist AI agents that learn from physical interaction. Nick has spent time at NVIDIA Research, Meta AI, as well as Berkeley AI Research, and received their BS and MS degrees from Technical University of Denmark. They were a recipient of the 2024 NVIDIA Graduate Fellowship, and their work has been featured at top venues in machine learning and robotics. The floor is all yours. If you can get started.
Okay, yeah, Rahul, thank you so much for the introduction and for the opportunity to come and talk about world models. So you might have heard world models a lot in academic society in the last couple of years. There's more and more attention and focus on world models and building increasingly larger world models. But a lot of this progress has happened in the industry. And so I want to focus on world models more specifically in academia and what people on an academic computational budget can participate. So first, before talking about world models, excuse me, let's talk about AI models more generally. So a lot of the more creative digital AI agents that we've seen already, like LLMs and VLMs, they're fairly general in the sense that you can snap a photo and give a question for like room decoration tips, and it's able to generate a response that kind of matches the question and the photo that you took. You can also prompt these models with text, and they're able to generate pretty high resolution images or videos that match your description. One of the key takeaways here is that it's usually a single model or a single algorithm that can be applied to a variety of different problems without the user of the algorithm or model necessarily knowing much about AI or the specific domain that they're applying the model to. This is a pretty new paradigm, and it's quite different from what we've seen, say, 5 years ago. So generally speaking, there's 3 key ingredients to building such a model. Usually we need pretty big, diverse data sets. Usually the data is scraped from the internet, like pictures and videos and text from the World Wide Web. We need scalable architectures, which in LLM world is usually transformers. The key thing about the architectures is that it needs to be scalable in the sense that it's able to consume these ever-increasing dataset sizes. And then I think the most critical part is that we need training objectives that are general enough, let's say next token prediction and language modeling, that we can take these models that we've trained on lots and lots of data and be able to apply the same model to new tasks by simply changing the prompting. So we don't quite have this embodied AI yet, but I want to talk a little bit about what are some of the components that might go into building such a model. And I want to focus specifically on world models because they are the models that allow us to reason about the physical world, much like LLMs can do planning in language space. And I would argue that predicting the future given the past is probably the most general objective that we can come up with in the realm of embodied AI. There's been some work in industry on this already, like 1X Technologies has prototyped a world model that is trained on lots of robot data from their specific robot. And here's a short video that is generated by this model. Similarly, Wave have come up with models like this for autonomous driving. This is a video of their world model, which is conditioned on a short sequence of frames and then a sequence of driving actions. And it's able to simulate what would happen plausibly if you took those actions in a real car. And Google DeepMind has done this as well for video games, where it's a single world model that is trained on lots of different video games, and it's able to generate short clips again of pretty realistic looking game dynamics, given, again, key commands. And one of the biggest things that make world models different from the typical video generation models we have is that world models are able to generate counterfactuals because they're conditioned on actions. So given the same frame, here you can see the Google DeepMind world model being able to generate different sequences conditioned on different actions, but all starting from the same frame. So this is what makes world models small neural simulatable worlds that we can train agents in. Most of the models that exist already are built in industry and are typically closed source. So we don't have access to the specific data that they used or the architectures or even the training details. So what I focus on in this presentation and in my research more generally is trying to crowdsource a lot of these same tools and data sets that people have been using in industry. And as a community, I think we've made a lot of progress on simulation tools already. We have good simulators like Mojoko, ISAC, and Manyscale that run fast, they're GPU parallelizable, and they generate a lot of data in very little time. We also have fairly good open algorithms. Lots of RL algorithms exist and are openly available, like Soft Data Critic, Dreamer, TD-MPC2, and many others. There's still more work to do here. I think the algorithms that we have are not quite robust enough to be applied out of the box, and they tend to still focus mostly on these single task environments. And arguably one of the things that we're lacking the most as a community is sharing the artifacts of the experiments. To give you an example, for TD-MPC2, our algorithm that we released a couple of years ago, we released more than 300 checkpoints, basically a checkpoint for every single experiment that we ran for that paper. And this is very unusual, but it has given a lot of people the ability to not have to recompute everything that we did. They can just take the checkpoint and use it for their purposes. And this makes research much more accessible. So we want to see more of that as well. And so these two parts will be the focus of today. So let's talk about how to build a world model. My definition of a world model is a model of the transition function of the environment, and meaning that it's a mapping from the current state of the environment and then also conditioned on an action, and it's able to map that to a future state of the environment. Because we're doing RL, we also usually include a reward function in the transition function. So we're predicting both the future states and also the future rewards. And given that definition, we can use world models to do planning, meaning that we can train a world model from environment interaction. This gives us an approximate model of the real world. And then we can sample a lot of different action trajectories and evaluate the rewards using our world model, and simply just select the action that maximizes this reward. The specific components of a world model, usually we have an observation space that might be low-dimensional states or images or even a combination of them. We encode the observations that we are given using some encoder. This is part of the world model. That produces some kind of latent representation that we can use to model the dynamics in the latent space. So typically we do all of our modeling in the latent space rather than in the observation space. The dynamics function here is a model of the transition function essentially, but in the latent space. So it's conditioned on the current latent state, and an action, it's predicting the latent state of the future. And then in order to train this model, typically in an end-to-end manner, we need some kind of supervision for this world model. And then also typically we have some downstream tasks that after training the world model, we want to use the world model for something. And This could be, for example, for supervision, it could be reward prediction. It can be self-predictions of predicting the future latents and comparing those to the expected latents. It could also be adding a decoder to the dynamics function and then using, for example, pixel differences or pixel reconstruction as your objective. So that's usually how you would train a generative model. So one of the things that differ between different algorithms is usually how you do your supervision and the different downstream applications. One popular way of supervising your model dynamics is a generative model. So this is, for example, a Dreamer. Many of you might have heard of. It's a world model that is trained to predict future frames given the latent dynamics. So it's a generative model that generates pixels, for example, if the state space is images. The models that I'm going to be talking about today are self-predictive models. An example of this is TD-MPC, which is my previous work. And it works similarly in most of the components of the world model, but the key difference here is that the supervision for the dynamics is different. The way that TD-MPC works is that we don't have a decoder. Instead, we're just comparing the latent embeddings that we get for our states when we roll out the model versus if you take those ground truth future observations and encode those with your encoder. And we're going to see some examples of this. But that's the key difference. One of the main works of my PhD was TD-MPC2. In this work, we took our TD-MPC algorithm that we built initially, the world model algorithm, and improved some of the different components in the model to make it faster to train, more accessible to people by making sure that you don't actually need a lot of domain knowledge to use it. And we've also made it scalable, which I think is almost a first when it comes to reinforcement learning algorithms. And so here specifically, when talking about world models and RL, by scalable, I mean that as we get more and more data and we increase the number of parameters in the model, we would expect better performance. This has not been historically the case in RL, but it has in areas like LLMs, for example. And the robust part here is what I talked about initially, that we want at least an algorithm that can be applied to a lot of different problems and domains without any specific user domain knowledge. So it should work pretty much out of the box. I want to talk first about how to do planning with a TD-MPC algorithm, the TD-MPC world model. Then we're going to look at how to build the world model itself and how to learn it. And then we're going to look at some examples of how to use it for actual problems. So the planning is pretty simple. It's more or less what I mentioned previously. So given an observation that we receive from an environment, we can encode that into a latent representation that we call Z here. And then conditioned on Z and a sequence of actions that we can sample from some prior distribution. That allows us to simulate futures, like future trajectories in the latent space of this model. And because our world model also has a reward head, we can predict reward for each of these steps that we roll out the model. Now, we can't feasibly roll out the model too far. So we also learn a value function that essentially just truncates the reward prediction here from the planning horizon and beyond. So the return that we're maximizing here is that the sum of rewards is the rewards for the planning horizon that we do plan, and then we use the value function here to bootstrap from the planning horizon and beyond. The way that we train the model is very similar. We have a data set of transitions or trajectories. This might be collected online, or it might be an offline data set that is provided to us. We sample a sequence, and then in that sequence, we sample a frame S1 here. We encode that into its latent representation, C1. And then conditioned on this latent state, we predict the optimal action the reward we would get, and also the value of the state. And then conditioned on the actions that we took in the data set, we can recurrently predict future latent states and all of their quantities as well. And so we can do this for a fixed number of steps. Now you'll notice that this world model is not yet grounded in the dynamics. So there's no component here mapping the latent space back to the observation space. The way that we supervise that is a little bit more implicit than a generative model. But as I mentioned previously, we minimize the difference in the latent embeddings that we have here. So for this specific example, if you were to take the embedding of S1, so C1, and recurrently roll out that latent state with our dynamics function, a few steps into the future, we get C3 here on the right. We would expect this embedding to be very similar to the embedding that you would get if you took S3 and encoded that with your same encoder into its latent representation. So this is the Sorry, I think I dropped for a second. You all hear me?
Yes.
Yep. Okay, great. Yeah, hopefully you didn't miss too much, but we would expect the embedding C3 that we get. Let me just share again. All right, sorry about that. We would expect the embedding C3 that we get from rolling out our dynamics in the latent space to be very similar to the embedding that we would get if you took S3 and encoded that into its latent representation using the exact same encoder. So this is the main source of supervision in the self-predictive and TD-MPC world models. And there's some computational advantages to this. It's much cheaper than having a decoder, especially if you work with very high-dimensional data like images or video. So purely from a computational perspective, this is a lot cheaper and more accessible for academia. You can write out the equations like this. I might skip that unless there's specific interest. We can come back to this. But essentially, it's a world model that is trained with these three terms, reward, value, and self-prediction objectives. And we just recurrently roll out this objective for whichever many steps we simulate for. So now that we've seen how this algorithm works, let's see what we can use it for in practice. You can use TD-MPC because it's an RL algorithm. You can use it for online RL. And in online RL settings here, usually we start from scratch. So we have an unknown task, the dog here. We want the dog to run, but we have no model pre-training. So we're starting from scratch in terms of model parameters. And we also don't have any data. So we need to collect our own data. And you'll see here that TD-MPC, it can iteratively collect data using our world model and planning with the world model. And then on the data that we get, we train the model gradually on this gradually increasing data set. And eventually, when we're at the 10 million steps, we have a working dog running policy. You'll probably notice that this dog is not likely to transfer to a real dog. It would probably break its ankles very quickly. This is kind of an example of RL over-optimizing the simulation a little bit. There's some joint angles here that I think are not entirely realistic in the simulation. But overall, it's an optimization framework that is very, very powerful for this kind of locomotion or manipulation or other problems. And crucially, this doesn't require any domain knowledge about dogs or even locomotion at all. And I think what's coolest about this is that even with a pretty slow simulator and no parallelizable environments, you can actually train this working dog policy in one day on a fairly old GPU. So this is definitely something that most people in academia can participate in. During this project that we did a little while ago, we took this RL algorithm in an online setting and applied it to more than 100 different tasks, spanning different simulators and domains that people in the RL community usually care about. So some examples are DM control and MetaWorld, and with ManySkill as well, MyoSuite, and some other domains. And if you recall our initial objective, we wanted a single algorithm that can solve all of these problems without domain knowledge and without any tuning of hyperparameters. So we're going to look at some single task RL results where we just apply our algorithm repeatedly for each and every task in our benchmark without any hyperparameter tuning. So it's a single algorithm, single set of hyperparameters applied out of the box on all of these domains. And so here on the left here, we have 6 domains that we split up the tasks in terms of which simulator or benchmark they come from. And we have some y-axis here, which is what we call a score. So it's the success rate whenever we have a defined success function. And otherwise, we just use the reward and normalize it. And we compare to some classic RL algorithms like soft as a critic. This baseline here is actually tuned to most of the different tasks. Dreamer V3 does not require hyperparameter tuning. It's been shown to work very well on, for example, Atari games, which are discrete actions. But when we applied it to a lot of these high-dimensional continuous control problems, it didn't really perform that much better than soft as a critic. We also benchmark against TD-MPC 1, which is the first iteration of our algorithm. This TD-MPC algorithm did require hyperparameter tuning. So for each of these domains, we did tune the algorithm to those problems. And then TD-MPC 2 here is the latest iteration of the algorithm. It does not require hyperparameter tuning, and you'll see that it performs pretty consistently across many of the different tasks. Especially compared to TD-MPC 1, you see that it's always similar or better, but without any tuning. So this is much more approachable and accessible for people. We also performed some offline RL experiments. So this is an example of a pseudo-scaling law for a small set of tasks. So we have 80 tasks here from 2 different problem domains. So we take these 2 problem domains, we collect a bunch of data. So like offline RL data. So exploratory, random, beginner policies, expert policies, collect a bunch of data, and then we train progressively larger models on this data set. And what you'll see here is that as we increase the model parameters, so the x-axis here is in log scale, you'll see that you get progressively better normalized score as well. And this is, to my knowledge, the first time that someone showed this in a purely offline setting. And I also want to highlight here that the second largest model that we trained with 48 million parameters is still pretty small compared to LLMs, but it's pretty big in RL space. And this model was actually trained in just 5 days on a single GPU again. So this is definitely also something that most people in academia can feasibly train themselves. You might be asking, so why is TD-MPC 2 better than TD-MPC 1, and why does it scale? There's a few key design choices that I want to highlight, and we did some ablations on things like the planning, regularization, invariance of the model. And these are all ablations on the same multitask dataset. And one thing that we notice is that if you do planning, the brown and the red bars here, you actually scale significantly better than if you were to take your world model and then learn a model-free policy using your world model. So there seems to be something inherently in the planning algorithm that exploits the world model more and squeezes out more performance than if you were to train a simpler model-free policy. But crucially, this only happens when you have large amounts of data and multitask setting and high-dimensional problems. We also add a lot more regularization to the world model. I would assume that as you increase the amount of regularization in the model, it becomes more robust to these quirks in the data. And especially when you have offline data, you might sometimes be out of distribution when you do planning downstream. And it seems like regularization is something that helps in that sense. And this bar plot here just shows that as you add more and more regularization to your model, you get better performance. There's one other trick that we use in the paper is that we, instead of doing continuous regression on the rewards and values, we instead use a discrete regression problem or formulation of the prediction problem. And the reason that we do this is that if you're working with RL data from many different tasks, the different tasks have widely different reward scales, and the expected values of all of those different states in the data set would also vary a lot. And so if you want to make sure that all the tasks are equally represented in terms of reward prediction, you need to normalize your rewards in some way. And the way that we do that is simply just model everything with discrete regression. So predicting which reward bin you would be in instead. And there's some mathematical tricks you can do to go back and forth between continuous and discrete, so you can still recover the original values. So those are some of the tricks. There's more tricks in the paper if you're interested. I also want to say that for this paper, we did a lot of open sourcing. So we released the code for training evaluation. I think that's pretty standard in the community. We also released our data set. It's a really large data set, 500 million transitions that we use for the multitask experiments. This is all open source. And we also released every single checkpoint in that previous figure that I showed. So this is more than 300 different checkpoints that are openly available, and anyone can use them. For example, if they want to benchmark against TD-MPC2, or if they just want to, if they want a policy that can generate demonstration data for the specific problem that they're working with, they can download any of these checkpoints. Now I want to shift gears a little bit and talk about more practical problems in the remainder of my talk. So specifically, assuming that we have this algorithm, TD-MPC, or a similar algorithm that has scaling and learns pretty efficiently, how can we use that to get more data, and how can we use it to solve practical problems in robotics? So firstly, if you think about data collection, we have a few different options. One of them is just RL interaction. Like I showed with the dog, we usually, as we get more and more interaction data, we're able to improve our policy. The problem with that is that it's very cheap in simulation to do, because our simulations generate a lot of data and it's pretty safe. But the diversity that we get from the data is mostly limited by the data that the simulation provides. So this gives us proficient policies for very narrow skills, but it doesn't give you the kind of diversity that we would expect from a world model. We can also collect demonstrations, for example, on real robots. This is pretty costly and time consuming. You need to buy all the hardware, and you also need to have humans collect all of these demonstrations repeatedly. This does give us more diversity. It's easier to, instead of building simulation environments, you can just buy a bunch of objects and manipulate those objects on a tabletop, for example. And it also provides stronger supervision, because we have a human expert that is trained to collect good demonstrations. We usually get more signal out of demonstrations than we do with RL interactions, where it's more like trial and error. So if we were to design a wish list for the training data for world models, I would say that we need a scalable data collection method. So we can't just scrape the internet, because there's no internet of robotics or interaction data. But what we can do is that we can have other methods of scalable data collection, or we can combine, for example, interaction and demonstrations to get more diversity. And so one simple idea that we tried is to, for a specific task, collect a few demonstrations and then do online interaction. And the reason that this is a pretty symbiotic combination is that imagine if you have a task here, like the one on the left, where you have a hammer and a nail, and you need to pick up the hammer using this dexterous hand and then hammer the nail into the board. This is not particularly complicated or long horizon, but if you are to do it with image inputs and sparse rewards, it's very likely that you would never be able to get a working policy if you simply start with random interactions. And so one example here of random exploration is the hand here doing some random motions, but it's very unlikely that this would ever pick up the hammer and hammer the nail. Human demonstrations, even with just one demonstration, you can already provide some learning signal to the algorithm. And humans are pretty good at hammering nails. So you get a lot more supervision. And one simple thing that we did is just to combine human demonstrations and RL interaction. So we built a simple pipeline here based on TD-MPC and TD-MPC2, where we collect some number of demonstrations, let's say 5 demonstrations. We pre-train our world model on those 5 demonstrations. And then we let our world model interact with the world after and practice the task more. And so as we collect more and more interaction data, we add that to a separate data set that we call a buffer. And then anytime we make gradient updates on our model, we just sample 50-50 from the demonstrations that we provide to the algorithm and the interaction data that it collected itself. And it turns out that this very simple idea is actually pretty powerful. So here's examples on real robots where we set up a robot in the lab. We have 3 RGB cameras. You can see one of them in the frame at least that provides high resolution RGB observations. And then we have a sparse reward signal that is simply detecting whether the task is successful or not. And we have a human collect 10 demonstrations for each task. And then after that, we do just 1 hour of autonomous interaction using our TD-MPC algorithm. So it's progressively training the world model and then doing planning to collect more data. And something that I want to highlight is that these policies are not perfect, but if you do just 1 hour of fine-tuning, it's a lot better than what you would get just from the demonstrations alone. Here is examples of 2 tasks, the bin pegging and the reorientation of the water bottle. And you'll see that if you do behavior cloning on those 10 demonstrations, you get about 20% success. We have pretty good signal in terms of solving the task. So the policy is able to solve the tasks if you initialize it very close to where it has been seen in the demonstrations. But if you venture outside of those very narrow state spaces and you have a new configuration, it doesn't really work out of the box. So that's mostly what we get by doing online fine-tuning, is that we take a policy that is already decent and knows how to solve the task sometimes, and then broaden the state and action space for which our policy is proficient. Now, how can we improve upon this idea? One thing is that while we have some demonstrations to provide supervision, we're still doing RL with sparse rewards. So one simple idea here is that based on those demonstrations that we are providing, can we use that to learn a dense reward function that would speed up the RL interaction phase as well? And for example, here, if you have a fairly short horizon task here, but a little bit more long horizon than what we saw previously, a task here where you need to pick up this peg and then insert it into the box, it's very unlikely that this would work with sparse rewards if you only provide reward when it's inserted. But if you have an improved recipe here where you coarsely define some task stages, say picking up the peg, moving it towards the box, and then finally inserting it, you can learn a dense reward function from demos by simply predicting which state you're in, here, one of these 3 stages. And it turns out that this dense reward function is good enough that you can run the exact same algorithm that I showed before and get pretty sizable improvements. And so crucially, you are learning the dense rewards from those 10 demonstrations. But as your RL agent interacts with the environment and gets more and more proficient, you can also train the reward function on that new data. So the reward function itself gets better, but also the policy gets better. And here's an example of a successful trajectory that we see here on the left. And then the plot next to it is the predicted reward using our dense reward function as a function of the time step. And so you see here that it's giving more reward when the peg is being picked up. And then when it's finally inserted, it gives the highest reward of 3. So this directly comes from the stage prediction. So reward of 3 here means that we're in stage 3, where it's inserted. You can do the same for a failure, and you'll see that it's able to detect when the robot fails. And eventually it gives a reward below 0 here when it drops the peg out of its reach. We do some benchmarking on some different simulatable environments. We have some tabletop manipulation, and we also have a humanoid manipulation benchmark. And the blue one here is the method with the dense reward function. You compare that to the orange one, which is the one that has sparse reward function. So that's what I showed previously, DR1. You see there's a pretty sizable improvement. Although you probably would get the same end performance if you were to run the same algorithms for long enough. But if you move back to real robots again, this would be a lot more desirable. On the different benchmarks that we have, we see a pretty consistent pattern that using this learned dense reward function is doing a lot better with this budget that we have defined than the other alternatives. The problem with this kind of approach is that we're still doing single task problems, and we need task-specific demonstrations for each of those problems that we're working with. So anytime we have a new object we want to manipulate, we would have to probably collect some demonstrations for that object. And one way to get around that would be to rely more on existing data sets. So in this last part here, I want to talk about how we can leverage human data as a prior for interaction in high-dimensional problems. The thing about humanoids specifically is that we often want our humanoids to mimic humans and human behaviors, meaning that we want them to be natural in their motions. And natural motions are pretty easy to demonstrate because humans are pretty proficient at being human-like. But it's very difficult to actually write a reward function, for example, of being human-like in code. So if you're working with locomotion problems like this, where you have a locomotion policy that is controlling a high-dimensional humanoid, you want it to be conditioned on images so that it can see what's in front of it. And you want it to be able to manipulate or run across these different randomized environments. It's a very complicated problem in itself, and you also probably want it to do that in a way that is natural, especially if you want to deploy it on a real robot. And the question that we ask in this work here is whether we can use existing vocab data to give the world model an idea of what is human-like. And we want to do this before we ever think about the task that we want to do downstream. The way we set this up is in a 2-stage pipeline. So first, we have a big human mocap data set of humans doing a lot of different motions. We import those motions into a simulator, Mujoko specifically, and then we train our humanoid here in orange to follow motions that we sampled from the data set. So we do some retargeting to this humanoid embodiment that we're working with, and then we're simply just learning to track those movements. And we do that with a single world model. We just do RL in simulation, learning to track all of these motions. And we train a single model on more than 800 different human motions. So this is all just RL, online RLs from scratch. Every single episode, we sample a motion and we give a reward that is proportional to how well we're tracking that motion. Now, given this tracking world model, we are not able to do downstream tasks downstream out of the box. We're able to simulate or like track all of these different motions, but we are not really capable of solving new problems. But what we can do is that we can save this tracking world model and now have a pretty good world model of humanoid motions that are natural and are good at tracking. We save this world model and then we can reuse it for new downstream tasks. Before showing that, I want to show just some tracking results. This is it's a little bit laggy for me, but it's tracking results for the single TD-MPC2 tracking world model that we trained here. So this is all the same model that is just conditioned on different motions. And it's not able to track perfectly, but it's doing a decent job. Now, in the second stage here, we take our pre-trained tracking world model. This is a model that is specific to the humanoid, but it's general in terms of tracking any kind of motion. And then we have a simple idea of just training a different world model that is providing those tracking conditioning to the tracking world model. So this is a more high-level world model that takes images as input. It has a task-specific reward signal, so it's trained on downstream tasks. And then the action space of this higher-level world model is simply to provide commands for this lower-level model to track. So they both take proprioception as input. The puppeteer world model also takes images and a reward function. And then it does online RL on these downstream tasks and essentially just learns to use the tracking world model to solve tasks. So this is the two-stage pipeline. The puppeteer world model we train individually for each task that we want to do downstream. So we're optimizing those tasks. But the tracking world model is fixed and constant across all of the different downstream tasks that we're doing. I hope that's somewhat clear. I'm not going to go too much into detail of the technicalities of training this, but I want to show some results on the puppeteer model, which is basically just TD-MPC, but with human data in this two-stage approach. And we can compare that to a RL algorithm like TD-MPC2 that is trained just on the downstream tasks without any human data in the pre-training. And what you'll notice here is that both of them actually run more or less the same, so they have similar reward, but one is definitely preferred by humans over the other, just in terms of how natural the motions are. And here's an example for a different task with hurdles. Again, the reward is pretty similar for these two policies. Actually, the one on the right is converging to a slightly higher reward. But in terms of naturalness, I would definitely prefer the one on the left. And if I were to deploy this policy eventually on a real humanoid, I definitely would prefer the one on the left. So to wrap up, I want to just summarize some of the key points that we discussed here. We've discussed a little bit about world models and why they're promising for this kind of generalist embodied AI. We have seen evidence that they're able to simulate a lot of different futures given the same initial conditions. They give us counterfactuals, which is really powerful if you want to do planning, for example. You can sample different trajectories and then optimize in that way. You can also use it to train policies, much like you would train in a classical simulator. We've seen that combining multiple different sources of data can be really powerful. And especially if you want to do kind of academic research on smaller scales with less robots and less time probably to collect demonstrations, providing some demonstrations and then just doing interaction after can be really powerful for this data collection pipeline. And the good thing is that all the new data that you're collecting by doing online interaction, you can feed back to your world model data set, and gradually you will have a bigger and bigger data set at your disposal. And at least just one idea for how to scale these kind of world model approaches to a lot more embodiments is that you could simply train tracking world models that are really proficient at simulating all of these different embodiments. And then you could train a big multitask puppeteer world model, for example, that knows the high-level dynamics and the specifics of the different tasks. And then it simply learns to control the low-level tracking world models for each of the different embodiments such that they solve the task that it wants them to solve. And so I want to end on a note, positive note, and just say that embodied AI has never been easier. This is a really good time to enter the field. The hardware is way more accessible and much cheaper than when I started my PhD. And we finally have policies, whether it's big VLMs or small world models like TD-MPC, that are able to solve fairly complicated problems with very little data. And so, yeah, I want to end and just say thank you to my advisors and all of the different collaborators that have worked on the projects that I discussed here. I'm also happy to take questions.
There is one question in the chat. Actually, two.
Let me see if I can open the chat. Okay, so one question from OT is, why would there not be a collapse if we have loss on latent embeddings of two different timestamps? Referring to the TD-MPC training, I believe. Yeah, so here, why is there not a collapse? There could be. I think there's two reasons that it doesn't happen in practice. One is that we borrow a little bit from the idea of self-prediction and vision domain, where people have been training models like BYOL that are predicting different versions of the same input. The way that we do it here is that we use a stop gradient on the future observation and that encoder. So S3 here is encoded with the same encoder, but then we apply a stop gradient so that the gradient only is back propagated through the dynamics modeling and back to the original state. And I didn't really explain that because I skipped over this slide kind of. But if you can see my cursor here, the first term here is the joint embedding prediction.
Hi, Nick, you're actually not audible. You've been dropping on and off.
Oh, is it better now?
Yeah, can you answer the question again? It was not clear. It was not audible.
Oh, okay. Let me just see if I can. Is this better?
Yeah.
Okay, let me try like this.
Can you go back to the training?
Yes. Okay. Yeah, so the question was why there's no collapse here when modeling the self-prediction objective. And we take some inspiration from methods like BUIL that has worked previously for images, so non-sequential. And the way that they do it in that work is that they have a very similar self-prediction objective, but where the target that they're trying to predict, they apply a stop gradient after that encoding. And that means that the gradient has to flow only one way back. We do that as well here. So we apply a stop gradient at S3 when we encode that, but not when we encode S1. So the gradients here will naturally flow back from the right to the left and then down to the S1 observation eventually. So that's one way to do it. Another reason is also that we're also doing reward prediction. And so when we're modeling the reward signal, that provides a different objective that also prevents this constant embedding collapse that you sometimes see in other literature. But because we have these two terms, we're both modeling rewards and also dynamics. We don't see the collapse.
Hello.
Hi.
Oh, actually, we couldn't hear you. You dropped out. Yeah.
Oh, you still can't hear me?
Yeah.
Oh. Some people can hear me, I think. Okay. I hope it's good enough that I can continue. If not, then I can write the answer in chat as well. The second question here is, how difficult is it to model a specific reward function? Is there a specific mathematical foundation, or is it mostly trial and error? I think there's some theory, but usually the RL theory that we do have lags behind the models that we're actually producing. So a lot of the theory is making assumptions, whether the reward function is linear or the model is linear, or some other assumptions like that. So I think that tells us a little bit and informs a little bit our decisions when designing algorithms and objectives, but it doesn't translate one-to-one. So in general, I would say that as an RL researcher, I tend to not change the reward function. I usually work with benchmarks where they're already predefined. And for most locomotion problems, those reward functions usually has somewhere between 1 and maybe 4 or 5 terms. So for the dog, it's just 1 term, which is forward velocity. For a slightly more realistic dog, or if you want to transfer it to a real robot, you might add some additional terms that minimize the energy spent, penalizes when the joint limits are reached, things like that. And so that's something that usually is important for real world robotics, but less important in simulation. For manipulation, it's a lot harder to come up with reward functions. So you can write dense reward functions, but they often end up being hundreds of lines of code. So what we do in our real robot experiments, all of the manipulation that you saw, we just use sparse reward functions. It's fairly easy to design a success detector, whether it's scripted or it's learned with supervised learning. And nowadays you can even use a VLM, for example, to you can prompt it an image and a question whether the task, for example, is solved, and then it can provide a binary signal on that. So those are all options. I would say for locomotion, it's a fairly easy problem. For manipulation, it's a lot harder. All right. Any last questions before we?
There are a few more questions. If you could see in the chat.
Oh yes, I see. Okay, so one question is specifically regarding the collapse here, whether I'm using a momentum encoder. We did do that in TD-MPC 1, but it adds a lot of extra parameters. So especially when we did the scaling part, it became kind of inconvenient to have these additional parameters that are just a momentum of the online parameters. So what we decided to do instead is to just reduce the learning rate on the encoder compared to the rest of the model. So the dynamics are moving faster than the encoder. parameters. And that's actually enough to get the same effect as the momentum encoder, but without the extra parameters. Are you learning the embeddings to predict also the reward, Q&A? Yeah, so everything is trained end to end, with except for the actions. We learned the actions just as a function of the latent embeddings. So that's a model-free policy that is learned in the latent space. And the function of this policy prior is just to speed up the planning process, because we want fast, real-time online planning. So that speeds up that process a little bit. Everything else that pertains to the world model itself is all learned end to end. And that's also part of why we don't have this collapse, because we're predicting both rewards and also dynamics. Have I seen if the TD-MPC2 architecture is stable without reward prediction? It's stable, but the representations are worse qualitatively. At least for the task of control. So because we're not generating future images, it's a little bit harder to evaluate the quality of the representation besides control. But if you care about control, you probably do want reward prediction or some other similar metric in there, just to make sure that the model and the policy is supervised on a way that is task specific. So purely from a compression perspective, for example, if you have a fixed amount of information that you can store in your latents, you want to prioritize the things that are relevant for your downstream task and control specifically. That's not something you would get if you remove the reward prediction. But if you leave it in there, you can actually learn very small models that are very task-centric and throwing away some other information. But you can fit a lot more information, a lot more tasks in very little parameters. So there's some trade-off there. The current trend is to investigate self-predictive models rather than generative ones. Is there another perspective, such as a hybrid approach, or any other alternatives that you know of? I would say actually in RL, there's more work on self-predictive models right now, just because they're cheaper. But in industry, I think all of the models that you're seeing are all generative, because they have access to more resources. And I think the recipe for training generative world models is very mature. You can more or less just take the same pipeline that you use for LLMs and VLMs and just apply it to world models, and you'll get something that works, but it's going to be very expensive to train. And so self-predictive models are offering more of interest to academia just because they're more accessible, and usually the models are much smaller. They require less compute to train to get the same performance. I think you could get something in between, probably, and that would be trading some parameters and some compute for more interpretability, for example. And also would help with things like learning the dynamics in a way that doesn't collapse or lose information. So I haven't seen much of work like that, but I think that would be interesting. Yeah, I hope that's a satisfying answer. If we encounter problems with distribution shift when training a multitask model and applying it to new tasks downstream. So I would say that we don't get a lot of zero-shot generalization right now. The models only train on 80 tasks, which is a lot from an RL research perspective. But if you compare that to the amount of data that you have in LLMs, for example, where you get generalization, I think we're several orders of magnitude away from that. And as a result, I think we get some signal that fine-tuning is better. So if you take a pre-trained model and you fine-tune on new tasks, even when it's cross-embodiment or cross-task, we do see some improvements, but it's nowhere near the point of being zero shot. How are the models different from MBPO? As far as I recall, that line of algorithms, they train a world model and then treat the world model as a differentiable simulator for policy optimization. So online on policy optimization using the world model. And I would say it's very similar. We basically just learn the world model in a very similar way, but then when you do the policy extraction, so saying going from a world model that is able to simulate the world into a working policy, there's many ways that you can go about that. You can learn, for example, just a self-directed critic policy using your world model. You can use policy optimization like PPO, or you can use a gradient-based method that differentiates through the world model. Or you can just do planning, which is what we do in TD-MPC too. I think we don't have a verdict on what is better. I suspect that it might be more nuanced, that it's depending on the specific problem and like the size of the model, for example. Some policy extraction efforts might be better. But yeah, I think for now, there's still an open problem.
Okay. Thank you. Okay.
All right. Yeah, maybe that's all. Thank you so much for all the
Okay.
questions
Yeah.
and
Yeah.
being
If
here.
I think, yeah. So if you have any questions, please free to reach out to Nick. I think he's happy to answer those questions.
Yeah, please send me an email. I'm happy to chat.
Yeah. Thanks for joining. It was great session. Thank you. Thank you, Nick.
Yeah, thank you for organizing.